in this lesson, we will continue to look at how to determine the shape of molecules. But I want to be clear, because we're looking at the shape of molecules, but we're also looking at the shape of bonds. All of our balloon models kind of do both of those at one time. So you've got to understand how to determine the difference between the shape of bonds and the shape of a molecule. And that's what this lesson is partly about. So we've been learning about shapes, molecular shapes and bond shapes. And it's important that you understand there are two different things, okay? Molecular shapes are not the same thing as bond shapes. So we have different balloon models to represent these things. Actually, the balloon models go to bond shapes more than they do molecular shapes. Although, bond shapes inform molecular shapes. Bond shapes, please pay attention here. Please pay attention here. Please give me your full attention here. Bond shapes help you figure out what molecular shapes are or should be. Your homework assignment was to make a balloon model for formaldehyde. The IUPAC name for this is not formaldehyde, but methanol, I believe it is. But its common name is formaldehyde. Most everybody knows this chemical is formaldehyde. It's the stuff you store animal parts in. Okay. If you were going to figure out the molecular shape for formaldehyde, you have to know about what kind of bonds are there. Okay? And we're going to go back to the sort of beginning where we learn how to put together covalent compounds doing an electron dot formula. So formaldehyde is H2CO. I want you to write now, as a class assignment, write the electron dot formula, sharing arrangement, Lewis dot formula, and Lewis formula for formaldehyde. So you're writing the electron dot formulas for all the atoms or elements here, then the sharing arrangement, then the Lewis dot formula, then the Lewis formula for formaldehyde, and I'm going to help you through understanding the difference between these molecular shapes and bond shapes. All right, to get these are the electron dot formulas here. To get the sharing arrangement, we're going to share electrons in such a way that carbon and oxygen can have 8 electrons when we're done, and the hydrogens can have 2. So, I will share these 2 electrons here, and these 2 electrons here, these 2 electrons, and these 2 electrons. So you can only share 2 electrons in a set. Okay? Now, once we've got this sharing arrangement now, and that's what this is now, is a sharing arrangement, we're going to do the Lewis dot formula. With the Lewis dot formula, we simply squeeze the electron dots between the element symbols. So here's the carbon, and I'm going to squeeze the 2 electrons between the carbon, this carbon and hydrogen, and now I'm going to do this one. Then I'll have 4 electrons between carbon and oxygen, and those lone pairs have to stay there. Okay, and that's the Lewis dot formula. Then for the Lewis formula, we're going to replace any shared pairs with lines, and only shared pairs. We don't replace any lone pairs. Now, these right here are this is a lone pair right here. This is a lone pair right here. It's not being shared between 2 atoms. This is 4 shared electrons. There are 2 shared pairs. 1 shared pair here and 1 shared pair here. So only the shared pairs get replaced with lines. So we need 2 lines because there are 2 shared pairs between the carbon and the oxygen. And the lone pairs just remain out here. All right? From that, then we want to learn how to do the 3-dimensional shape. And we're not even at the point of doing the bond shapes yet. Okay? I want to show you how to do 3-dimensional shapes. Okay? Now, sometimes it's easier to figure out the bond shapes first. Okay? So I'm going to go down here at the bottom, and let's look at the bond shapes here for this molecule. So this is a double bond between this carbon and oxygen. So here's a carbon, and here's an oxygen. We're going to say that's where the nucleus is located, okay? And we are going to need, if I have a double bond, then I have a sigma bond and a pi bond. Sigma bond and a pi bond. Now the sigma bond is, by definition, that bond that lies directly between the nuclei of the 2 atoms. So I need a bond that goes directly between these 2 atoms here. And we looked at this last week and found that that was a kind of a wiener shape, okay? Cigar shape, okay? Single balloon shape, whatever you want to call it. The symbol for sigma is this, it's like a circle or a small letter O with a switch on the top, okay? Like that. And then around that, we're going to need a pi bond. Now, the pi bond, as I explained last week, starts out as 2 p orbitals that are not hybridized. A p orbital on the carbon that's not hybridized, and a separate p orbital on the oxygen that's not hybridized. I'm going to do this really lightly. Okay, and there's a p orbital on the carbon and the oxygen that's not hybridized. And these then are going to kind of reach out to each other like this. Now the reason we need to have a pi bond that's something like this is because we have 2 electrons in this bond, okay? So when we bonded the first time between 2 atoms, there's 2 electrons there. The second pair can't be close to the first pair. Remember that 2 electrons can be in the same orbital, okay, if they have opposite spins. And since I can only have 2 opposite spins, then I can only have 2 electrons here. So this has 2 electrons. Any other 2 electrons cannot be near this. So we have to have a bond that's somewhere outside of this region. They're going to be pushing apart from each other, but still be drawn into this space between the 2 carbon nuclei because those protons are drawing those electrons together. Protons are positive, electrons are negative, and so opposite charges are going to be pulled together. And so what's going to happen is this second bond is going to form from these unhybridized orbitals. Remember, we had hybridized orbitals we looked at last week. We made a model of the sp3 hybrid orbitals. Now we're looking at an unhybridized orbital. So this is not going to be sp3 hybridization anymore. But these 2 orbitals are going to join together and form a pi bond that goes around the sigma bond. Okay? You can think of this in a lot of different ways. I like to think of it as the hot dog is here and the bun is here and here. So let's erase the pencil marks I have here, and you can kind of hopefully clearly see what this bond is going to look like. So when you did your balloon model at home for homework, you should have had a single balloon that goes in between where the 2 knots are located. Where the carbon and oxygen are located, they're knots. Okay? And you should have a single balloon between them and a balloon that goes around them like that. Okay? Now, over here on the oxygen end of things, there's 2 lone pairs. Okay? Those lone pairs are hybridized orbitals. They're not bonded to anything, so we have to show those as a single balloon shape. Okay? And the way we've done that already several times is to have a balloon shape like that. And I need a second one. Let's see, blue marker. So I'm going to put this one kind of behind it here.
So hybridized means they're not bonded to anything?
No, hybridized means you can have a bond or you might not have a bond. Hybridized just refers to the fact that the bond shape is different from the original s and p orbitals we had in the last couple of units ago. Okay? So now, the unhybridized orbitals, if they're not bonded, Tyson, if they're not bonded, they'll be a single balloon shape. Now, this bond here came from a hybridized sp2 orbital, and this one came from an sp2 orbital. So this sigma bonds always come from hybridized orbitals. So sigma bonds and lone pairs always come from hybridized orbitals, okay? Sigma bonds and lone pairs always stem from hybrid orbitals. Okay? Pi bonds always stem from unhybrid orbitals. Okay? Now then, over here on the other side of this carbon, there are two lone pairs. There's two single bonds here and here. Okay? So we need to have two single bonds coming off this carbon. And the single bonds we've done is a single balloon shape. It's always a sigma bond, just like this one. And there's your two bonds to the two hydrogens up here. Both of these are sigma bonds. And there are two electrons in those sigma bonds. Now these pi bonds right here, this is all one pi bond. So we had a single p orbital going this way originally. A single p orbital has two antinodes. That's what was sticking up and below that I just erased with the pencil marks here. And this one had a p orbital here with two antinodes. And so when we join those together like this, this double thing is actually one bond. So you have to know that even though this bond here, this green part, is in two parts, it's one bond. Okay? So this is part of the same pi bond. If that p orbital was, let's say, py, then this is going to be pi y. Both of these are pi y. And you can say that's the antinode and that's the antinode. Okay? Got that? So that's how we relate that then to the unhybridized set of orbitals we did a couple of units ago, several weeks ago. Okay? Now, then once we see this, then we can go back up here and see that there's only three things sticking off this carbon. Now when we're doing molecular shapes, and that's what we're going to be doing here, these are going to be molecular shapes in this section down here. I'm going to be doing molecular shapes. And these are bond shapes. So we said originally, when we first started talking about this, that there's a difference between molecular shapes and bond shapes. Well, this is the bond shape here. That's what a bond looks like. Now we're going to look at what's called the molecular shape. And so what I want to do is define the atom around which I want to determine the shape. Well, the shape of this molecule is determined by whatever the central atom is. And in this class, mostly we're going to be using simple molecules where there will be almost most of the time anyway, a clearly identifiable central atom. Sometimes you've got to look at one atom in the structure at a time. Sometimes there's more than one to look at. But right now, there's just one central atom that determines the shape. Okay? So the carbon's going to be our central atom around which we're going to have a shape, a 3D shape. Now this is where you need a pencil. For right now, you don't need it, but you will need it for the next shape. So if there are three arms, if you will, this double arm is still one arm. Got it? This acts like one arm coming around the central atom. Even though there's more than one balloon, it's still one arm, one direction coming off the carbon. And so there's one arm coming off this carbon. Even though there's 4 electrons there, it's still one set. Okay? So we have 3 arms around this central atom. Now, I want you to stop and think. I want you to imagine. I want you to dream this in your head. I want the movie to run in your head. I want you to imagine this. What angle do I need between these 3 arms that will get them as far as I possibly can from each other?
A triangle?
It's kind of a triangle. So what angle is that going to be? If it's an equilateral triangle and where this is the center, huh?
60 degrees.
It's not 60 degrees. No, what's a full circle?
360.
360. If I divide it by 3, what do I get?
180.
No, 180 is half.
Um,
Huh?
not
90 is 4. God, this is not hard. 360 divided by 3? Come on. Yeah, 120. My gracious.
I was thinking half. I was expecting to be right.
All right. So 120 degrees. I need 3 arms 120 degrees apart. Okay? Because that will get those sets of electrons. Now look, this set of electrons is kind of grouped together. Okay? Like I have them kind of grouped together in this bond here. Okay? This set's grouped together, and they're grouped together in this double bond here. All right? So this set of electrons, even though the electrons are kind of pushing apart from each other to get the double bond here, they are also pushing apart from this set and this set. So they want to be as far apart as they can be. So these 4 electrons are kind of pulled in here, but they still want to be as far apart from these as they can. So we want them 120 degrees apart. Okay? So this set of electrons, what I'm going to have here, is going to be as far apart as it can be from the next one. That looks like something like this. Okay? Now, if you want to buy a protractor and do this, that's fine. Okay? But if you can't do it visually and you're going to draw 90 degrees instead of 120 degrees or something pretty close to it, then maybe you need a protractor. Okay? Or something that will help you with these. You need to know what 120 degrees looks like, what 90 degrees looks like, what 180 degrees looks like, and what 109.5 degrees looks like. Okay? So up here on the Lewis dot formula, not the Lewis formula, the Lewis dot formula, I have a pair of electrons trapped between hydrogen and carbon, another pair, a separate pair between this hydrogen and carbon, and 4 electrons, a set of electrons made of 4 between carbon and oxygen. Now that means there are 3 sets for the terminology of figuring out 3-dimensional molecular shapes. Okay, 3 sets. This is a set, there's a set, there's a set. This set has 4, and those 2 sets have 2. So on the end of this arm here, I'm going to put 2 electrons. On the end of this arm here, I'm going to put 2 electrons. So on the end of this arm, I need to have how many? 4. Okay? Now, this is the first step in figuring out a molecular shape. It's not the end of the process. And we're going to call this, now this is has a name. We're going to give this a name, okay? It's kind of a triangle. What we call it in chemistry is trigonal. And since this is kind of flat, if I had this 3-sided thing, it'd be sitting flat on the paper here. We're going to call it planar, like a plane, okay? So trigonal planar. And we'll call this an electron pair shape, okay? All right. Then from this shape, we need to draw the same thing over again. Now, we talked about this on Friday a bit with a different shape. This one we need to draw exactly the same. So we have a carbon here, and we need to have these 3 arms. Now, don't put any electron pairs on here yet, because you need to make sure if you aren't using a pencil that you put your electron pairs on here in pencil. Now, if you're doing it all in pencil, that's perfectly okay. All right.
What is this going to be called?
This one here?
No, the other one.
This
No,
one.
but, okay, you see, like, it says molecular shape up there. What is that one going to be?
This is a trigonal planar electron pair shape.
Okay, but up there it says molecular shape.
All these down here are going to be molecular shapes. Okay? Or at least that's the process for figuring them out. The final shape we get to will be the actual molecular shape. Okay? All right. Now that we've drawn the exact same shape, we're going to replace the electron pairs with the atom symbol if and only if they are shared. If and only if they're shared. So is this pair of electrons shared with something? Yeah, it is. With a hydrogen. So I'm going to replace that with a hydrogen symbol. Is this pair of electrons shared with something? What's it shared with? A hydrogen. Is this set of 4 electrons shared with something? Oxygen. Okay? And we can erase the lone pairs if you're doing this in pen or something. If you didn't, you could erase it before you started and put it on there as you go along. All right? Now, since when I put the atoms on the ends of the arms here, I don't have any more lone pairs remaining, this is going to be our final molecular shape. Once you go through the process and you no longer have any lone pairs left over, then you're finished with the molecular shape. Okay, so this is then the same name as this because we didn't have to erase, get to any points where we got lone pairs left over. This is trigonal planar molecular shape. Okay?
So why do we have to go from the dot back to the...
Question is why we have to go through these dots before we get to this?
Yeah.
Okay. It's not so much of a problem with this particular molecule, but some of the other molecules, if you don't do this process, you're not going to realize or be able to focus. Most students, vast majority of students, can't see in their mind the lone pairs that change the shapes. Okay?
And can it only go up to 4 dots on each side?
No, it can have up to 6 because we can have triple bonds, which we're going to get to either probably as homework today. Okay? All right. Now, let's go back then and look at a couple of other things we did molecules for, okay? We did this one already, right here. So listen, we found that for ammonia, the molecule of ammonia, there was a lone pair. When we put all the hydrogens on the ends, there was a lone pair left over. Then the next drawing, we got rid of the lone pair. This is where it's important to go through this step before we get to this step. And it makes a trigonal planar shape. Water worked out the same way. Water here had 2 lone pairs. We had to draw exactly the same drawing and then erase the lone pairs to figure out this is bent and not linear. If you don't draw in the lone pairs and then erase them, my experience teaching all these years tells me you will draw a linear shape when it's not linear. Okay? So let's take a second and just go and do one of these two. You want to do water or ammonia?
Ammonia. Water. Water. Water.
All right. Everybody for ammonia, raise your right hand. I see 1, 2, 3. All right, for water, raise your left hand. 1. Well, all right, we're gonna do water. All right. So I'm going to stop right now and let you work on the electron dot formula, sharing arrangement, Lewis dot formula, Lewis formula for water. And if you can, try to do the molecular shape. Well, we did it already, but I want to show you how to go through the steps anyway, okay? All right. Here's the sharing arrangement. We have 2 electron pairs to share. Squeeze the electron dots between the symbols. We get the Lewis dot formula. Lone pairs remain. Lewis formula then has the shared pairs replaced with a line. Lone pairs remain. Then we need an electron pair shape. That means we're going to go back here and look at how many sets of electrons there are around the atom that forces the shape to form. Okay, and that's the oxygen here. It's the central atom in this case, the atom we're interested in. Okay, so around oxygen then there are 1, 2, 3, 4 sets of electrons. Okay, all the electrons shared between any 2 atoms and all the lone pairs are the sets in this context. Okay? So a set for figuring out three-dimensional shapes is any set of electrons. All the electrons share between two atoms, and it's also whatever lone pairs there are. So there are 1, 2, 3, 4 sets here. Okay? In our formaldehyde, there were 3 sets. This set of 4 electrons is all the electrons shared between these two atoms. That makes up a set. All right. If I have 4 sets, then I need what's called a tetrahedral. So I need one arm that goes up, one arm that comes out at 109.5 degrees, a little less than 120, a little more than 90. Then I need one that's coming out like this to form an arm that's coming out toward you, and one that's tucked in behind like that. Okay?
Ooh, I did it so close.
Now, the first thing I'll do is an electron pair shape. The electron pair shape puts only electron pairs on those arms. So there's 4 sets, 1, 2, 3, and 4. And so that's a tetrahedral. So this is a tetrahedral
Hold on, I have a question. The little triangle
electron
shape?
pair shape. Okay, so sometimes, most of the time I've drawn the dotted line above the triangle shape, but this time I didn't, it doesn't really matter. It really has to do with perspective. If you've done art, you know what I mean by perspective. Yes, there are dots with a dotted line. Okay? Now, all of these are the process for finding molecular shapes, not bond shapes. These bonds are the Wiener shapes, remember? Okay? We're not showing bonds here. All right, now, the next step then, you need to do in pencil. Okay, the next step you need to do in pencil, that's to draw exactly the same drawing here. And I'll switch these two this time. I'll put the dotted line above. Okay, and put my electron dots out here. What I want to do for the modified electron pair shape is only put atoms on whatever number of pairs of electrons that are shared. So there's 2 pairs here that are shared with hydrogens. Okay, so I need to replace 2 of these sets of electrons with hydrogens. Okay, so I'll put a hydrogen here and a hydrogen here. It really doesn't matter which 2 you put it on. Okay, this is going to stay, and that's going to stay. And actually, everything is going to stay the way it is here now for the modified electron pair shape. We need to draw this over again to get to our molecular shape. Okay, draw this same shape over to get the molecular shape. Now, this still has those 4 arms. So this is still tetrahedral. This is a tetrahedral modified electron pair shape. Now, to get to the molecular shape, we're going to redraw this drawing here exactly the same. Redraw this drawing here. So when we started with this one, we redrew the electron pair shape and then modified it. Now we're going to take the modified electron pair shape, redraw it here, and modify that to find the molecular shape. So, do it in pencil. There's your oxygen, hydrogen, hydrogen. There's the arm that's swinging out toward you. There's the arm that's going behind. So listen, this is what's important. This is the critical part. You redrew it again. This is where students mess up. They just sort of start skipping over steps, and they get it all wrong. Please listen to me. Please follow my plea. Do not skip steps. It's when you skip steps you make mistakes. If you do this enough, you will be able to skip steps. But right now, I doubt anybody in here is ready to do that. There might be 1 or 2, but don't assume you're that 1 or 2. Okay? That assuming in this case might result in some bad results. So we redrew exactly the same thing, and we're going to erase the lone pairs. Okay? All right, now what we have left then is this with a hydrogen. There's the oxygen, there's the hydrogen. And we have, because we followed these steps, figured out that this is a bent molecular shape. Okay? There are only a few shapes, well, I shouldn't say a few because a little more than that. There are a handful of shapes that you need to know from memory and be able to figure out, okay? So, you need to know what a tetrahedral is. And if I were to list one of the atoms as A, B might be here, B here, P here, and B here. That's a tetrahedral. You need to know what that is. Okay? Out of a tetrahedral, if we eliminate one of these arms because we've got a lone pair on there, then we've got this. And this is a trigonal pyramidal shape. Okay? If we eliminate two of these arms, then we've got that bent shape we just did. Okay? Just give it a minute. Hold on. So if we go back to our formaldehyde, we had a trigonal planar shape. All right, pay attention. If one of these arms is a lone pair and we eliminate it, the resulting molecule is also bent like this one. Let's say we eliminate that one right there. What remains is a bent molecular shape. Okay? So I'm not going to redraw bent. All right? And then finally, we have a linear shape. So what is that, 4? There are more shapes in this, but in this class, these are the ones you probably only need to know. Okay? Now, what we're going to do is, as a class, you can find one partner to work with, and between the two of you, you're going to figure out electron dot formulas, sharing arrangements, Lewis dot formula, Lewis formula, then the molecular shape, going through the steps we talked about here, and finally do a balloon model for carbon dioxide. Okay? You're going to build a carbon dioxide balloon model. Yes, CO2. All right, so you are working on the models, that is to say the drawings and the three-dimensional balloon model shape for carbon dioxide right now in class. Just so you know, for homework, you're going to do the same thing for hydrogen cyanide. Okay, now, listen, pay attention. So you are working on a balloon model then for carbon dioxide right now in this class. Okay? I'm going to give you just a little bit of help here. I'll try to help you understand. Now, for some of you, thinking in 3 dimensions is really going to be hard. Please stop playing with the balloons long enough for me to talk. It's going to be really hard to think in 3 dimensions because some of you are not used to that. You're so used to seeing things in 2 dimensions like on this piece of paper or on this computer screen. Okay? Up and down is 1 dimension. Side to side is another dimension. Coming out toward you and back behind, that's a 3rd dimension. If you're used to seeing it on paper and a TV screen and a computer screen, Marasia, then you may not be used to thinking in 3 dimensions. How many of you ever done or played with a Rubik's Cube? You know why that was invented? It was invented by a college physics professor, Trey, please pay attention here, by a college physics professor to help his physics students think in 3 dimensions. And so you're having some struggling here because you're not used to that. If you're an artist or have taken art, or if you're an athlete, you shouldn't have any problem thinking in 3 dimensions because that's part of what you do in both those domains. But I want you to think this way. If we have a carbon atom right here in the center, please pay attention, because carbon in this molecule, carbon dioxide, is the central atom, the atom around which everything has to be built to find a molecular shape. then think of a sphere. So that you could think about that if you want to kind of put it in these contexts as if carbon is the center of the Earth and this is the Earth. Okay? So we got one side of the Earth over here. I'm shading it in as if the sun's somewhere up here, the light's somewhere up here, which it is. So let's just say for us that we're right over here on this side of the Earth. See where I'm pointing? What's the furthest I can get from this point and still stay on the surface of the Earth? And what, anybody know what's over here? That same spot on the other side. So that's like for us somewhere east of China, I think. Now pay attention. I still hear people talking and playing with balloons and not paying attention up here. So if I have my pair of electrons over here, or 4 sets of electrons for the that I'm sharing between the carbon and the oxygen over here, what's as far apart as I can get those pair of electrons? Huh? What's the furthest place on this sphere I can get the second set of electrons? The other side over here. Alright? What kind of angle is there between here and here, with this being the center? 180 degrees. It's really, just think about it that way, okay? So imagine this, that the carbon atom, or whatever atom is the center of everything here that we care about, is the center of this planet Earth. And if, I don't know, this is kind of not a great version of a globe, but let's say we're right here in South Carolina. The furthest away you could possibly be would be the opposite side of that, which is somewhere down in Southeast Asia, okay? That's about as far apart as you can be. That's 180 degrees from each other. If the center atom, the atom of interest, the very center of this is right in the center of this ball, then that's 180 degrees. This is as far apart as 2 sets of electrons can possibly be. So if we have a sphere, and this is the outer energy level, the valence level where the electrons are located, this is where those hybrid orbitals are going to be located, then at the center of the sphere is the carbon of interest. In this case, it's a carbon. It might be some other atom at the center, but then the farthest part you can possibly get is on the opposite sides, okay, for this kind of molecule, where you only have 2 sets of electrons around a central atom. So, one more time, here is a sphere, okay, actually half a sphere, okay, so I'm going to look at it this way, and if the carbon atom is located right here in the very center, the furthest you can get those sets of electrons apart from each other would be here and here. 180 degrees, a straight line from the two sets of electrons through that center. Okay. Now, if this were 3 sets of electrons, then it'd be 120 degrees apart. So here, up here, and say down here somewhere. Okay. That would be different. But this is for what we're looking at today for carbon dioxide. Is for 2 sets of electrons as far apart as they can be around a central atom that would be right here. So build your models, please, and do your drawings.